Hey programmers, I'm Alvin from CoderByte, and today I want to teach you about Big O analysis. So this is going to be the first video in a series on data structures and algorithms, and there's really no better topic to start with than Big O. But before we jump in, just want to let you know a few things, right? So in this video, I want to give us an introduction to Big O analysis, and what I want us to take away is really like the practical implications of Big O. What we're going to do is kind of avoid any of the heavy math analysis in this video. We may go over that stuff in the next video, but for now, I want to get a nice intuitive understanding of what Big O is and basically how to put it to good use. So there are a few goals I have for us in this lesson. The first thing I want to do is, of course, describe the motivation behind Big O, right? Why do we bother learning it, and how do we actually use it in the real world? Also, I want us to explore the rules for simplifying Big O. This is something you're going to have to do a lot in your technical interviews. And finally, I want to step through some practical examples about how we can derive the time and space complexity of some given code snippets. All right, so let's jump right in. So the first big question we need to answer is, why do we use Big O? Well, as a software engineer, our goal is to, of course, solve problems. And for any given problem, there could be many solutions. And as a software engineer, I want to make sure that I implement and choose the best solution. And so we have Big O as a framework that we can use to really judge and compare different solutions so we can figure out which one is the best. And so at this point, another big picture question comes to mind. What does it even mean when we say that we want solutions that are better than others, right? What does it even mean for a solution to be better? Well, when it comes to software engineering, or more broadly programming, we really want to consider our programs and our solutions in terms of the resources that they use up. And in general, we're really concerned with two types of resources. That is, we love to write solutions that use the least amount of time to execute, as well as the least amount of memory. And you may hear these referred to as time and space complexity, right? In general, we want to minimize the time and space complexity of our solutions. So at first glance, things may seem straightforward because it seems that time and space are two things that we can definitely measure, right? In the case of time, I could just maybe have a stopwatch and measure in milliseconds or seconds how long a program takes to finish. In the same way, I could measure the amount of space that my program uses in things like kilobytes or megabytes. However, there's a massive problem with that line of thinking. For example, let's just look at time complexity. Let's say I had the same program and I ran it on two different computers. We can expect to see a different amount of elapsed time when it comes to that program's execution, right? Imagine if I ran the same program on an old computer from the 80s versus a new laptop from the modern era, right? I kind of expect the better, more modern hardware to perform much quicker. To make matters worse, even if you ran the same program on the same computer twice in a row, you can still expect to see some variance when it comes to the amount of time it takes to complete those programs, right? At any point in time, our computers are running hundreds or even thousands of background processes. And of course, these background processes are not typically something we have a lot of control over. And unfortunately, they will affect the execution of the program in question, right? So it's very, very hard to just measure the outright like milliseconds or even seconds that a program takes to run, right? It's never going to be something very, very consistent. Overall, we have to face this problem of how can we ever control for any differences in computer hardware and environment when we try to measure the speed of our code. So let's say you're not totally convinced by my argument here. It's always healthy to be at least a little bit skeptical. What I'll do is spin up a little experiment and we can actually see this principle in action. Alright, so here we are in my text editor on my local machine where I have some code set up. So I have a very simple program over here. It's just a function that takes in an array of numbers and will just return the total sum of the numbers in this array, right? So over here I have this array initialized, and I also am going to take the elapsed time that it takes to actually execute this function. So to do that, all I have to do is take the time right before I call my function. I'm going to call my function in question. I'm going to get the time right after my function's done executing. Then I just take the difference to get the elapsed time in milliseconds. So let me go ahead and execute this program. Looks like I get an answer of 752 as a sum of this array, and it finished in 7 milliseconds. And I wonder what happens if I run this again a few different times. Second time I got 5 milliseconds. Next time 5 milliseconds, 6 milliseconds, and you can already see that I have a lot of variance when it comes to the elapsed time of running this same piece of code on literally the same machine again and again. So hopefully you found that detail useful, and now you see why we can't just use seconds to measure the amount of time a given solution takes to execute. And how do we actually solve this issue? Well, we use Big O notation. And so Big O notation gives us in a way that we can really objectively describe the efficiency of code without the use of any concrete units, right? So we won't measure time in terms of milliseconds or seconds. We won't even measure space in terms of megabytes or kilobytes or even just bytes. Instead of using real units to measure time and space, what Big O does is really just analyze the time and space in terms of how it scales with the size of the input. What's also really great about Big O is we really care about the worst case scenario. And this is actually a really great thing because in general, the best case scenario isn't really something we can be safe to assume. And if we prepare and optimize our code for the worst case, that overall leads to a very resilient solution that performs well or reasonable under all types of circumstances. All right, so now that we have that background analysis out of the way, let's actually use Big O to analyze a very, very simple function. So here I have a little code snippet in some JavaScript. So let's step through this basic code just to make sure we're all on the same page, right? All this function does is take in an array of some numbers and it'll return the average value of those numbers. And so how did we solve this one? Well, we just create a sum variable, initialize it to 0, and I'm going to be adding into that sum over time. Using a for loop, we just iterate through every number in our numbers array, and for every number, we just add its value into the sum, being sure to actually grow the sum, right? So we're going to accumulate the grand total in that sum variable. After I'm done adding every number into my sum, I finally just divide that total sum by the quantity of numbers I had in the array, right? And that should give me my final answer over here. So this is some really basic code, and we can actually use it as a nice way to practice the initial mechanics we're going to need to actually perform an analysis on this function. And so in this example, we'll focus on just analyzing the time complexity of this code, and in a separate example, we'll go ahead and look at how to analyze the space complexity. The first thing I want to do is recognize my argument, right? I know Big O is all about focusing in on how things scale. So my input here is an array. And what's the size of the input here? Well, it's really just going to be the length of the input array, right? You can imagine if I gave you more numbers in this array, it would take longer to execute than if I gave you fewer numbers. What we'll say is we'll define n as the length or the size of the numbers array. Now that I've considered that argument, I'll just take inventory of the different lines in this code and how they relate to the size of the input that I just defined, right? So let's take a look at some trivial lines. So honing in on just 2 and 9, if I look at line 2, that's just a very simple variable assignment. On line 9, I just have a nice division, just some simple arithmetic. If I reason about those lines, I know they execute exactly once, right? No matter the size of my input array, line 2 and line 9 happen once, or in general, they happen a constant number of times. In other words, if these two lines only execute a constant number of times, then they actually won't affect my analysis and I can basically ignore them. That means, of course, we should turn our attention to the for loop. And you guessed it, this for loop will contribute basically the entire time complexity. So let's break down the different segments of this for loop so we can make sure that we're all on the same page, right? So I know that a for loop consists of multiple statements. Let's start by looking at this statement over here. I know that that statement is just the counter initialization for my for loop, and it only happens once at the very start of the for loop. So I know that that's not really going to depend on the size of the input. That happens once always. If I look at the rest of my code, that is this condition check that will happen on every iteration. This increment does happen on every iteration. And of course, all of the code inside of the body of the for loop also happens on every iteration, right? And if I look at how far I'm going to iterate, I'm going from 0 all the way up to the length of the numbers array, right? So basically, the number of iterations of this for loop is basically exactly the size of the input. So I know that this for loop makes n iterations. And if I think about what happens on a single iteration, there are about 4 things that happen, right? This condition, this increment, and these 2 lines. Those are like 4 steps. So we couldn't say that there are n times 4 different steps overall, where n is the length of the numbers array. However, because Big O is really only concerned with the size of the input, which would be n in this case, we actually get to drop this 4, right? We can drop any of those multiplication of constants over here. So overall, something we can say is that this function has a O of n runtime where n is the length of the input array. So I know what you're thinking, how can we just drop that 4, right? That seems kind of suspicious. Really, it's just the case that that's exactly how Big O works, right? Big O is only concerned with how the performance of our algorithm changes with the size of the input. And actually, a huge advantage of having that dropping of constants is that when we actually end up with our final complexity, it's very compact and easy to compare to other solutions. And so I think understanding how to simplify time complexity is really, really important. In other words, if you were in a technical interview scenario and you were asked what is the time complexity of this solution, if you had said O of 4 times n, I wouldn't really take that as a proper answer, right? In general, you want to be giving your big O notation in simplest form. And so really the only correct answer here is a time complexity of O of n, where n is the length of the input array. Along with that, I also think it's really important in your answer to include how you're defining the size of the input, right? So here I said n is the length of the input array. In a separate video, I'll talk about how to actually define your variables if you had multiple arguments. But for now, what I want us to do is master how to simplify big O notation. Luckily, this isn't too difficult because there are really two hard and fast rules that you can always fall back on. So looking at our very first rule, the first thing I'll do is define what I call the product rule, right? And so to practice this product rule, we actually don't need to look at some code. What I can do is just give you some unsimplified big O notation, and then we'll simplify it together according to the rule, right? But let's take a look at in general what this rule does. So for the product rule, what we say is if the big O is the product, which is like the multiplication of multiple terms, we can drop the constant terms. Again, constant terms are like static numbers, numbers like 1, 4, 5, basically anything that's not a variable, we consider a constant term, right? So how can I put this into action? Well, let's go through an example. Let's say I gave you this big O notation. I will tell you that it's not simplified. This is exactly the scenario we had in that last code snippet, right? This reads O of 4 times n. I know that 4 is a constant here, right? And I can actually drop that term. So really the answer here is, in simplest form, just O of n, we say. So that's pretty straightforward. Let's look at another one. Let's say I gave you big O of 512 times n. You know that that can also be dropped, right? No matter how big that constant number is, it's still a constant, so you can totally drop it if it's multiplied to something else, mainly multiplied to your actual input variable, right? So 512 times n really just gives us O of n still. Leveling up a little bit. So let's say I gave you a third example and I asked you to simplify O of n over 3. And looking at this one, maybe this doesn't immediately ring a bell, right? I described this as the product rule, and you know that the product is really a multiplication, but here I have a division. But if you know some very simple math, what I can do is rewrite this division in terms of a multiplication. In other words, n divided by 3 is really the same as 1/3 times n. And it's still the case that I'm multiplying n by some constant value, right? 1/3 is still a constant value. So I'm allowed to drop it, and n over 3 overall can still yield an O of n solution. Let's say I gave you 5 times n times n. Notice I have multiple things here. You should be immediately able to recognize that I can drop this 5, so that's easy enough. And then from there, you actually can't simplify this further, right? You have to keep both of these n's. Again, if you're familiar with some very simple math, whenever you have a variable multiplied by a variable, we're really just saying that that variable is raised to the second power, right? So we can say O of n to the second power, or another way of saying is O of n squared. Please don't be confused here. In n squared, the 2 is not a constant I can drop, right? I'm not multiplying by 2, I'm raising n to the second power, right? Remember that n squared means n times n under the hood, right? And I can't get rid of either of these n's. So I think just for funsies, let's go ahead and look at a final example over here. What if I ask you to simplify O of 765? The first thing you should notice is there's not really an input variable here. What I can do is simplify this quantity of 765 to just O of 1. We also call this constant time. So I think the product rule is pretty intuitive. All you have to do is recognize what is a constant multiplier, and then you can just totally drop it. And luckily, there's only one more rule we're going to need to learn how to simplify any big O notation, and that is the sum rule. The sum rule is a little different, right? And so for the sum rule, if our big O is the sum or addition of multiple terms, we can only keep the largest term, and we're allowed to drop all of these smaller terms. Let's go ahead and step through some examples of this. So let's say I gave you an unsimplified big O notation of O of n plus 1000. So according to our sum rule, what we do is we choose the biggest term over here. So first, let's just see how many different terms we have. Looking at this code, we only have 2 different terms, so it's not too bad to see. I have the n term and also the 1000 term. And among these 2 terms, I choose the one that's bigger. And that really means I choose the one that's bigger in terms of n. Remember that this 1000 is actually not that big because it's just a constant value, right? It doesn't depend on the size of n. So really the n over here is going to be the winner, which means overall our big O complexity is just going to be O of n, right? I always choose the single biggest term. Looking at another example, let's say I gave you an unsimplified big O of n squared plus n. You already recognize that there are two different terms here, right? The n squared and the n, and we just choose a term that's bigger, which would be the n squared, right? And if you're not really aware of what would be bigger here, you could just try plugging in some reasonably large values for n. So for example, let's say n was 10. It's a big enough value in this case. If I did 10 squared, that would be 100. Otherwise, this right-hand side would be just 10, right? And so I would just take the n squared over here. So the final answer is O of just n squared. Switching gears to another example, let's say I gave you an unsimplified big O of this thing, which is n plus 500 plus n cubed, or n to the third power, plus n squared. And again, you could probably by now quickly recognize that the winner here is just the n to the third power, or n cubed. And so the final answer here is just O of n cubed. Notice that we're allowed to drop literally every value that's smaller than n cubed, right? So really take this rule to heart. So now that we understand both the product rule and the sum rule, we can actually put it all together, right? To simplify something fully, all you need to do is apply the product rule followed by the sum rule, and you'll be good to go, right? So this is actually super duper straightforward. Let's look at an example. Let's say I gave you the unsimplified big O notation of this thing, which is 5n squared plus 100n plus 17, right? So I think it's easier if we apply the product rule here first. So what I do is just drop all of my constant multipliers. So I should drop the 5, I can drop the 100, and I can turn that 17 to just a 1. So that gives me this, right? N squared plus n plus 1. Then among these three terms, I choose the biggest one, utilizing the sum rule, which is just the n squared. My final answer is O of n squared. Looking at another example, let's say I gave you n over 3 to the 6th power plus 10 times n. I can apply my product rule first. So I can simplify n over 3 to just n, right? And I can simplify this 10n to just n. So that should just read as n to the 6th plus n. And I just choose the bigger term among these two terms. And that just gives me a final answer of O of n to the 6th power. All right, so I think we have this bit of theory down pat. Let's actually utilize it to actually derive a time complexity out of some fairly complex code. And now you're going to realize why I explored those kind of pen and paper mechanics separately. So I want us to focus on the time complexity of this code snippet. Probably the first thing you'll notice is this function actually doesn't solve any, realistic practical problem. It's just some arbitrary code, but it does have a pretty cool time complexity that we can work out. That way we can understand how to put these mechanics to use no matter the circumstance. So where should we start here? Well, if we're talking about big O, then we care about the size of the input. Let's start by at least understanding what the input is, right? Here the input is just a number. If I give you a larger number, you'll probably recognize that overall this code is going to act a little slower, right? Because I use n, or the argument, as the bounds for these loops. But with that, let's actually analyze these loops in isolation, right? So looking at the very first loop over here, I'll refer to it as like the A loop. If I look at this A loop, it iterates starting from 0 up to, but not including, n over 2, basically half of n. So if you look at just this A loop, you may recognize that it makes about n over 2 iterations. However, in terms of big O, we can drop that division by 2, so we recognize that this for loop has given us a time of O of n. Now we just have to look at the other for loops over here. So just focusing in on this B loop, I'm only considering this B loop in isolation, so I'm not going to look at any of the code inside right now. If I just consider line 6 alone, that also gives me O of n time, right? Just simply iterating from 0 all the way up to n. If I look at now the C loop in isolation, that C loop also gives me O of n time, right? It basically does the same thing. But here's where I have to put things together. If I look at the B and C loop together, right, I have n iterations, and on every single iteration of that loop, I run n iterations again, right? So really the pattern here is if you have nested loops, you're doing a multiplication, right? This is n times n, right? So looking at this second chunk of code from 6 through 10, that gives me n squared runtime. So if I consider this code in totality, the first loop gives me n, right? And the second loop gives me n squared. Because this first for loop is totally separate from those nested loops, I just add these terms together, right? So I have an n plus n squared, and at this point, it's just what we did before. How do you simplify that sum? Well, all you do is grab the biggest term. So you know the answer here is just n squared, where n is the size of the input, right? The input number. Here you see that we only care about what really slows down the code, which is just the nested loops, really subscribing to that big O philosophy. All right, so let's keep it rolling and look at another code snippet. So I want us to derive the time complexity of this code. So at first glance, this is another function that takes in a number as the input. So I'll define n as a number I'm taking in. So looking at the very first for loop that utilizes I, it actually iterates a constant number of times, right? It starts at I equals 0, goes up to I is less than 3. Notice how it does not depend on my input n. So that may not factor too much into my final time complexity over here. But if I go down a little more and I look at the inner loop, the j loop, by itself, it iterates about n times, right? It starts at 0, goes all the way up to j is less than n. And when I consider both of these loops together, I have nested loops like before, I would just happen to multiply their complexity. So I guess at first glance, we may think that this is 3 times n, right? However, we know we can simplify that to just n. And looking at the final for loop at the bottom, looking at this k loop, this also just iterates a constant number of times, right? Although 10,000 is a fairly large number, it's really no comparison in terms of what n can grow to become, right? So I would actually also just ignore this second separate loop. So taking inventory of all the loops we have in play over here, the first set of nested loops gives us basically 3n. In our complexity, and that second loop that uses k, which is separate, means we add its iterations, which just looks like 10,000. And of course, this is just the unsimplified big O complexity. We know that once we simplify things, we will just end up getting a n as our final time complexity, where n is the input number. Pretty straightforward stuff. So taking a look at another example, how can we analyze the time complexity of some code that actually uses multiple functions, maybe like a helper function? For code with multiple function calls, all we do is really the same type of analysis, right? Just really methodically tracing through our code, right? So I know that the first function it's going to be called is boom with an argument of 10. That would actually be the one where I consider the input variable, right? So I'll define n, my variable, as my input number into boom. So let's look at the code inside of the boom function. We'll consider first the I loop over here. It iterates a constant number of times, which we know in the long run isn't going to factor into our time complexity too much. But on every iteration of this loop, we run the bam function. Let's go ahead and trace through what that bam function does. Looks like we're going to pass in the same number argument n. So it's passed in as m over here. And if I look at this code, all it does is iterate m number of times, so really just n number of times, right? So really, when I see this code over here that calls bam, this single call will give me n iterations, right? I know that when I consider the entire loop together, that is this whole chunk of code, it's going to give me 3n iterations overall. If I look at the rest of the code inside of the boom function, that is this second loop, it iterates 10,000 times once again. So considering everything as a whole, I have 3n over here plus 10,000 over here, which overall gives me 3n plus 10,000, which of course just simplifies to simply n. It's really the same type of complexity like we had in the last example. So hopefully from those 3 examples, you have a good basis for which we can use to analyze time complexity, but let's move our attention to some space complexity analysis. Now, it's really the same type of logic. However, this time we're not concerned with the number of steps we take. Instead, we consider how much space we use. So we consider things like variables, and especially objects that grow, things like arrays, objects, or even things like hash maps, right? And so let's look at this function over here. It's actually the same function from our very start of this lecture. It's a calculate average function, and what I want to do is analyze any variables that I create. So let's consider a few things, taking inventory. If you look at this initial variable of sum, it's only going to be created once, right? No matter the size of my input array, I only create one sum variable, so that's not going to affect my space complexity too much. In the same way, I have another variable. Looking at this one over here, this counter variable is only initialized once for the entire for loop. And going even further to the body of this for loop, if I look at this inner variable on line 5 where we say let number equal an element from the numbers array, although you know that this line is going to execute on every single iteration of this for loop, technically once this single iteration is over, we're actually going to free up the memory for this number variable, right? So as this entire for loop runs, it's not as if each of these number variables is going to persist in memory. Overall, we only use one variable over here, right? So overall, I have 3 different variables that would kind of give me an O of 3 space complexity, which I know I can simplify to just O of 1. So this solution for calculate average does not use up any additional space, it uses constant space. So before we go any further, it's worth mentioning that when software engineers refer to the term space complexity, they are typically referring to any extra space that a solution may use, not including the space consumed by the input array. Obviously, here we expect someone to give us an array of n numbers. We don't actually include those n numbers in our space complexity analysis, right? We're interested in space complexity as the additional space our solution requires to compute. Now let's ratchet up the difficulty a little bit. Here I have another function. It takes in an array of some elements. And so you can already recognize that my input here of n is going to represent the length of this input array. And if I kind of analyze quickly what this function kind of does overall, is it takes some input array and it returns a new array where I have every element appearing twice, right? So my original array is ABC, my output array is AA, BB, and CC. And if I look at the implementation of this code, I want to pay special attention to any variables, but especially this array, right? Does that array grow over time? And how does that array's growth relate to the input array? So let's consider this new array variable. And where do I actually add elements to this new array? That would be inside of the for loop here when I do my new array dot push, right? So I know that this for loop is going to iterate n number of times, right? It's going to iterate once for every single item inside of my items array. And then for every single item, I actually push 2 instances of that item into my new array. So you can probably imagine if this for loop iterates n times, on every iteration we push 2 things, overall we're pushing 2n things into that array. And that would actually be the amount of space that this function consumes. Luckily, you know that 2n using our product rule, it just simplifies to a complexity of O of n, right? Where n is the length of the input array. All right, so that's how we should analyze space complexity, but we can take this even further by analyzing the time and space complexity of recursive code. So in this lecture, we're going to do a simple example, and I promise in further videos down the line, we'll go over some really intense code. But for now, let's just get some bearings over here. When we analyze the complexity of recursive code, the time complexity is basically the same logic, but for our space complexity, we should consider the space taken up by the recursive calls on the call stack, right? Those actually have to factor into our analysis. So taking a look at a easy little recursive function over here, it's a very toy function where we take in some input number, and our recursive call is going to call the same function on one less than that number. In other words, if someone were to call our zoom function with an initial argument of 10, it would just console.log all numbers from 10 down to 1 and then finally lift off once that number really hits 0. As always, as I reason for the time complexity of this recursive function, I consider how the number of steps relates to my input number over here, which is n, right? So on any particular call to this zoom function, I'm going to do this conditional check over here. That's like one step. And I'm going to do this console.log. That's another step, right? And I guess you could also consider this recursive call over here, right? So these 2 steps are kind of just going to give me a constant number of steps, right? It's just about 2 steps, we'll say. But then I have a whole nother call over here. And what you have to do for this time complexity is think about the kind of recursive chain of events, right? And so the mental picture I have is when we call zoom with an initial argument of 10, that 10 in turn is going to call zoom on 9. Then 9 is going to call 8. 8's going to call 7, and you can see the running pattern here. This happens all the way down to essentially 1 and also finally 0, at which point we would have printed out liftoff, right? Looking at this chain of recursive calls, it's really going to be just a linear chain, right? I'm going to have a number of recursive calls that is equal to my original number argument, right? So if I call zoom with 10 at the very start, I'm going to have about 10 recursive calls, and that would actually be my time complexity. So here we'll say that our time is going to be O of n, right? And now let's consider our space. If I look within this function, I don't use up any arrays or any other objects. But like I said before, I must consider the recursive stack space used, right? So here, if I'm going to have n recursive calls and they all have to use up a little slice of the stack, then that also gives me O of n space, right? When you analyze the space complexity of recursive code, what you really have to think about is how many stack frames or how many recursive calls do I need to make before I actually hit my base case here, right? I know in this example, if I were to call zoom with initial argument of 10, I would have to make 10 recursive calls or have 10 stack frames before I bottom out on my base case. So there we have it. We have O of n time and O of n space, where n is the input number to this zoom function. So let's take a look at one more recursive example. And in my experience, this is actually an example that kind of trips up students a lot, although it's pretty related to the very last one, right? So I almost have the same function shape, right? It's still a recursive function. It does print out some numbers. And it still takes in an initial number of like 10 in this particular example. My base case happens where n is less than 1, in which case I print out blast off. If I look at my recursive call, after I were to print out my current number, I call the same function with n minus 2. If you recall, in the previous one, we did n minus 1. Really, the only difference is now I do n minus 2. How does that affect the actual time and space complexity of this code, right? So in this function, I'm just really decrementing by 2 upon every recursive call, right? So if we call 10 top level, I know 10 calls 8, 8 calls 6, 6 calls 4, and of course this pattern continues all the way down to like 2 and then 0, right? If you look at the pattern here, I basically have half the number of function calls compared to the last example, right? So if n is my input number, I'm going to have n over 2 function calls. And you know that if that's going to be the time complexity, I can simplify that to just the time being, of course, O of n. And it's actually the same case for the space complexity, right? The space has the same argument as last time, where my space complexity is also O of n, right? So don't be fooled by, just manipulating the recursive case by subtracting 2 or even subtracting 3. Those are all going to give us a O of n time and space complexity in this example. So this is a really foundational recursive analysis example. In further videos, we'll go over more involved recursive functions, and we're going to really use this as like a baseline of comparison. So if we're able to understand why this example is still O of n time and O of n space, you're going to be really set up well for our further lessons. Cool, so let's move to our final bit for this lesson. I want to actually solve a practical problem and use our analysis to optimize it. So let's say we're given a problem, and here our prompt says me to write a function called unique that takes in an array of elements and returns a new array containing just the unique elements. So I only want to have the elements appearing once. So taking a look at the given example, if you were to call unique and pass in an array of cat, dog, rat, dog, cat, and bird, we should return a new array containing each of those elements only once, right? So I don't have any duplicates in this output array. So let's take a look at one straightforward solution that we'll use as our baseline. Right. So in this solution to this problem, what we do is we create a new array that we're eventually going to return. Then we have a for loop to iterate through the input array. And now for every element of the input array, we just check, hey, is that element not already included in my new array? And if it's not already there, then I can go ahead and just push that element into the new array, and that'll ensure that it's not a duplicate. Of course, let's say the element is already inside of the output array, then this condition would be false, in which case I don't add it to my new array, so I won't force a duplicate. So it would give you unique elements as output. However, why don't we take a look at the complexity of this function? We already know how to do that. What we should do is really just analyze things at scale with the size of the input. So starting with our time complexity, I'll start by looking at this for loop. Immediately I recognize that this for loop directly depends on the input array, so it directly depends on my complexity variable, which would be n over here. Now, if I look at the code inside of this for loop, things are actually a little involved, right? If I look at this if statement, it is checking a condition. However, what I have to also do is consider when I use a method like includes, right? It's an array method. I have to consider, right? Is this call to includes also going to consume some time, right? In general, searching through an array would require a linear scan, right? It would just have to technically iterate through the new array to check, does it include my given element? In other words, if I were to imagine the code that implements includes, although it's a built-in library piece of code, I could probably imagine there being a for loop inside of that, right? So this would actually give us n time as well. We can already see that, hey, if I have this for loop iterating n times and technically a line inside of it also iterates n time, that would give you n times n complexity, right? So the time complexity here would be n squared. In terms of the space complexity, it's straightforward. It's just going to be the space used up by our output array, which is this new array over here, which is simply going to be exactly n, right? So let's take a closer look at what we really just said here. Honing in on just the space complexity, we say that O of n is the space complexity because you can imagine in the worst case scenario, the input array already contains unique elements, in which case basically the output array is identical, right? So it would be O of n. And so looking at the time complexity, we're probably wondering, can we do any better than n squared? Luckily, since we did a pretty thorough complexity analysis, we can probably understand the bottleneck over here, right? That bottleneck would be this array includes over here. If I consider the other thing that contributes to my complexity, that is this for loop that just iterates or touches every element of the input array, I think that's a necessity, right? There's probably no solution that you can ever come up with that solves this problem without actually touching every element of the input array, right? That wouldn't make any sense. However, maybe we can forego this costly operation over here, right? And so since we've identified this as the bottleneck, how would we potentially rewrite this one? So here's another solution to unique using a different data structure instead of an array to store our initial unique values, right? So looking at this different variable I have initialized at the top, it uses a set. So if you're unfamiliar with sets in JavaScript, what they are is a hashed data structure, and they also give us uniqueness baked in. Why don't we actually take a moment to take a quick detour and really understand what this set can do. So here I am in my JavaScript REPL, and I'll just create a quick little set. So I'll say my set equals new set, kind of similar to that code. And sets are pretty straightforward structures. Main operations I'll be concerned with is like adding members to the set. So I can say my set.add. I'll add maybe a number, favorite number, 42. To add some other numbers, so I'll add 100. You can really add whatever you want. So add the string, add my name. We'll say Alvin, right? So there I have some elements in my set. Let's say I tried to add an element that's already there, like 100. If I actually do that and I look at my set, it actually remains unchanged, right? So one really nice characteristic about sets is it's already kind of required that your elements or your items in your set are going to be maintained as unique. And then from there, maybe other operations you might find useful is like to check for existence in a set. So does my set has the number 42? That is true. Does it have Alvin? That's also true. Does it have Cindy? That is false, right? So very straightforward API for a set. And maybe something else that you'll find useful is, let's say you had a set, right? Here it is. And you wanted to convert it into an array. You can just do array.from my set. And that's a very kind of idiomatic pattern for sets. So jumping back into my snippet over here. So there I have my set, and in this solution, we still iterate through every element of the input array. We still grab it over here, but this time we just add that element into my set. And actually adding an element into a set, because it's a hashed data structure, is going to give you a constant time operation, right? Just inserting into a set is constant time. And the upshot is, from that alone, it's already going to maintain uniqueness for me, right? So really, if I analyze the cost in this solution, right, this for loop gives me O of n, and that entire for loop, including the code inside it, is just O of n overall. But if I look at the final return line over here, this return line basically converts the set into an array, because that's really what they asked for in the final result. That would actually be O of n as well, right? And so if we consider the entire time complexity for this function, that first for loop, like we said, gives us n time. And then that last line of converting the set into an array would be an additional n time. However, it kind of works out nicely here because this conversion of the set into the array, that is not nested in the for loop. Because they are kind of operations that are one after the other, I add them together, and you know that n plus n is the same as 2n, which if you simplify that just gives us O of n, right? And so overall, we really optimize this code. We reduce the time complexity from O of n squared to now O of n, and we also kept the space complexity the same, right? It's still the case that our set and even this array that we're eventually going to return would at most be n elements. And so what I want you to take away from this walkthrough is how we use our complexity analysis to really identify what was the bottleneck in our original solution, and then we can actually target it for a nice refactor, overall getting a more efficient solution. And so the last thing I think we'll do in this lesson is to actually run both of these solutions that we came up with. I always think it's important to always run your code to make sure it actually works, and hopefully we can kind of see the huge impact of analyzing our code and how time complexity actually plays a role. All right, so here we are back in my trusty text editor, and here I have laid out both of our solutions. So I have the O of n squared solution over here, just as it was before. I just renamed it as my unique slow function. Then I have our n function over here, our unique fast function that of course uses the set. And then from there, I just have some basic boilerplate code down below. So I know that I need an array to give as input to both of these unique functions. And I'm going to generate those randomly. So here I just have it populating my random array with 100 random numbers. And those numbers are integers from looks like 0 up to 99, right? And what I do is I take times or take the elapsed times for both of these functions, right? Just like we did earlier in our lesson. Let's go ahead and run this code. So this will be my unique experiment. Scientist, I guess. So there I see my output arrays. They're going to be identical. That's exactly what we expect. Now if I look at the time, elapsed time for both of these, looks like my n squared took 7 milliseconds. My fast solution, my n, looks like rendered as 0 milliseconds, so probably not even a full millisecond, which is awesome. Let me run that again. We have 7 milliseconds versus 1 milliseconds. So we already see that our fast solution is noticeably faster than our other one. And we can notice that this discrepancy gets even larger as I bump up the size of my input, right? So instead of 100 numbers, let's do like 100,000 for the culture. Let's see what that looks like. So it looks like 16 milliseconds versus 4 milliseconds. Let's go crazy over here. Let's add a few more zeros to that. And it probably will still be the case that our fast solution is noticeably faster, right? Our n squared is 714, whereas our n is 171. Awesome, so hopefully you now see the value in really analyzing our code. So to wrap up this video, what did we learn? Well, what we did was we used Big O to compare solutions by how they scale with the size of the input. And also along the way, we really denoted some hard and fast rules that you can use to simplify your Big O. And whenever you're in an interview scenario and forevermore, you should always simplify your Big O notation. In the next video, we'll continue our talk on Big O and talk all about more diverse code and the different complexity classes that they give us.